Third page. Factor affecting vapor pressure. First is temperature. Vapor pressure increase with the rise of temperature. Later on we will also discuss the equation by which we can explain this factor. Number 2 is nature of liquid. Nature of liquid again means the force of attraction. Like here is an example. Vapor pressure is directly proportional to 1 upon force of attraction. For example, if we have a water and ethanol. In water there are stronger hydrogen bonding, then so vapor pressure will be less. Strong the force of attraction, less will be the vapor pressure. If the vapor pressure is more than partial pressure, then condensation takes place. And if the vapor pressure is less than partial pressure, then the evaporation takes place, because vapor pressure is the maximum value of partial pressure. Now, there are 2 points. PA0 represents the vapor pressure of pure liquid A, when only one liquid is there. Not means pure. PA means pressure, vapor pressure. PA only, when not is PA only, when that is the partial pressure of A in the mixture. That is not pure. When we mix a 2 liquid, then we will represent the PA, the partial pressure of A. Suppose we have another component B, then we will represent the partial pressure of that component as PB. So vapor pressure of any liquid does not depend upon the amount of liquid. Will not depend upon the amount of liquid. Will not depend upon the volume of the vessel and shape or size of the container. Means these are the volume of the liquid, amount of the liquid, volume of the vessel, shape or size of the container. On these factors vapor pressure will not affect. Now we have a classification of substances on the basis of vapor pressure. So this is important. Number 1, volatile substance. Number 2, non-volatile substance. Volatile substance means having definite value of vapor pressure. In case of volatile substances, P0 not equal to 0. So these are water, methanol, ethanol, benzene, toluene. So these volatile liquids, they generally will come in the numerical problems. Number 2 is non-volatile substances. So non-volatile substances having no tendency for evaporation. So in these cases, P0 equal to 0. So solids are generally non-volatile substances. So in the maximum numerical problem you will find that urea is given, or glucose or sugar. These are the solids which are non-volatile. So these are the formula of this: urea molecular weight 60, glucose molecular weight 180, and sugar molecular weight 342. So generally keep these values in mind for the numerical problems. Next is the variation of vapor pressure with temperature. So generally when we increase the temperature, the vapor pressure will increase. So this variation is represented, this is given by Clapeyron equation. No need to do the derivation, just you must know about the equation, that how these are related. Like this is the general equation, Clapeyron relation: d ln vapor pressure upon dt equal to delta H upon RT square. Delta H is enthalpy of vaporization. When 1 mole of liquid changes into 1 mole of vapors, that energy required is known as delta H. R constant, T is temperature. So as temperature is directly proportional to vapor pressure, so you can integrate this. So it become integration d ln Vp equal to integration of delta H vaporization. So this dt come this side. So after integration you will find this ln Vp equal to minus delta H by RT plus K. K is a constant. And next this it become this is a, so this ln Vp is y-axis, and this delta H 1 by T, then 1 by T will be on x-axis. So this is a graphical representation, a graph between ln Vp versus 1 by T. It's a straight line with a negative slope. Slope here is minus delta H upon R. So at two different temperatures, suppose T is T1, vapor pressure is P1, at T2, vapor pressure is P2, you can drive the equation like this, and finally we get this reaction. Log P2 upon P1 delta H upon 2.303 R 1 upon T1 minus 1 upon T2. So this is very useful equation that will be used in many numerical problems that are related to Kp, Kc, Vp, Kc, Ka, Kb, dissociation constant, acid base, and K equilibrium. So next is the vapor pressure of solution. Now solution is formed when solute is added to the solvent. So when solute is added to the pure liquid, it becomes solution. Now this solute that may be volatile, that may be non-volatile. So there are two cases that we will discuss one by one. So case 1 is when vapor pressure of solution containing non-volatile solute. This is the first law of this chapter, Raoult's law. Raoults, Raoult's law. Vapor pressure of solution containing non-volatile solute. Non-volatile means solid. So if we have a solution, there are two components, solute and solvent. Solute is represented by B and solvent is by A. So let's see the nature. Nature of solute is non-volatile. Nature of solvent is volatile. Physical state. Because it is non-volatile, so solute will be solid, maybe sugar, urea, glucose, etc. And nature of the solvent will be liquid. Vapor pressure, solute, because it is non-volatile, so vapor pressure will be 0. Solvent is because vapor pressure is of the solution, such type of solution is only because of the solvent, so it's PA, not moles. Moles can be calculated from the given mass, number of moles of solute, Wb upon Mb, number of moles of solvent, Wa upon Ma. Then we can calculate the mole fraction like this, Nb upon Na plus Nb, X is equal to Na upon Na plus Nb.